right, welcome infrastructure admins to this explainer. Today, we're zeroing in on a very specific but absolutely crucial subtopic for your upcoming certification, NCP-MCI 75-1.4 CVM sizing. I'm going to be your guide as we navigate the exact rules and requirements for sizing your controller virtual machines. If you're prepping for the Nutanix Certified Professional Multi-Cloud Infrastructure exam, mastering these specs isn't just, a suggestion, it's a strict requirement. We're going to break down the exact baseline numbers for AOS 7.5 and AHV 11.0 so you can walk into test day with total confidence. Sound good? Okay, let's dive right in.
So, here's our game plan for today. First, why CVM sizing matters. Second, a detailed walkthrough. Third, exam traps and edge cases. And finally, key facts to memorize.
Section 1, why CVM sizing matters. And as you might guess, it is absolutely crucial for performance. Getting your sizing right is literally about cluster survival. The Controller Virtual Machine, or CVM, is a dedicated VM running the Acropolis operating system, AOS, on every single hypervisor node. It's essentially the beating heart of the entire Nutanix architecture. It provides all that Nutanix-specific functionality and handles the heavy lifting for storage. If you starve the CVM of resources, well, you're starving your entire host of storage I/O. It's really that simple. There's a quote from the Advanced Administration Guide that really hits the nail on the head here. The CVM's performance depends heavily on the allocated computational resources. Adequate computational power is essential to ensure efficient operation, especially in denser systems. I want you to really lock in on that phrase, adequate computational power. Things like total storage capacity, how frequently you run data protection snapshots, and the advanced features you enable. All of these demand dedicated compute overhead. Undersizing your CVM, that's a critical failure point before your guest VMs even boot up. Moving into Section 2, a detailed walkthrough looking at real-world scaling. Let's ground all this theory in some real-world infrastructure deployments. Take our first example, a robo, or remote or branch office deployment. These are often single-socket edge nodes operating at the absolute bare minimum requirements to save on cost and physical footprint. But then look at example 2. This is a completely different beast, a high-performance NVMe cluster. This setup is running Blockstore with SPDK enabled to really accelerate those ultra-fast drives. Now, you absolutely cannot treat these two environments the same. Why? Because bypassing the kernel to talk directly to NVMe drives takes immense dedicated computational power. That high-performance setup requires a massive resource bump just to keep the CVM running effectively. To put that into perspective, let's look at the exact baseline numbers pulled straight from Table 16 of the Advanced Administration Guide. For that ROBO and edge platform we were just talking about, you need 6 logical cores and 20 gigs of vRAM. But look what happens with a default x86 server. For a standard all-flash node up to 48 terabytes, that baseline jumps to 8 cores and 32 gigs of vRAM. And if you're building dense storage, we're talking capacities over 135 terabytes. For that, you're looking at a staggering 14 logical cores and 40 gigs of vRAM just as a starting point. Definitely keep these scaling steps in mind as we start layering on more features. So, what happens when we introduce modern storage features? Well, in AOS 7.5, new installations deploy Blockstore on HDDs by default. But to really push those high-end NVMe and Optane drives, Nutanix uses SPDK, the Storage Performance Development Kit. Notice the crucial requirement here. Deploying SPDK instantly raises your CVM memory requirement to at least 48 gigabytes of RAM. And catch that last point, SPDK is not available for HDD-only configs. So the second you combine Blockstore, SPDK, and NVMe hardware, your CVM sizing rules change dramatically. Okay, Section 3, exam traps and edge cases. Let's learn how to avoid those common pitfalls. Now, test writers absolutely love to test automated behaviors, so let's walk right into the minefield. Listen to this scenario carefully. What happens during foundation if you allocate less than 48 gigabytes to a CVM in an NVMe cluster? Imagine you're setting up a cluster with Optane or NVMe SSDs. You plan to run Blockstore with SPDK, but during the foundation installation process, someone accidentally sets the CVM memory to, let's say, 32 gigs. What happens? Do you get a failed installation? Does the whole host crash on boot? Well, here is the definitive answer. Foundation auto-updates the CVM memory to 48 gigs. It actually has a built-in safety net. If Optane or NVMe SSDs are available in your cluster and the CVM memory is set lower than 48, Foundation automatically steps in and overrides the mistake just to make sure the system can actually function properly. Pretty smart, right? But wait, because here is a classic exam trap. That auto-raise behavior strictly applies to Blockstore with SPDK. The Advanced Administration Guide explicitly states if you are not deploying SPDK, ignore this requirement. So a question might mention a cluster completely packed with NVMe hardware, but specifically state that SPDK is not being used. If there's no SPDK, that 48 gig minimum rule and the foundation auto-raise, they simply do not trigger. Do not fall for that one.
All right, here's another massive edge case for your CVM sizing, the number 256. Starting from Foundation version 5.3 onwards, there's a hard cap on how much memory Foundation will automatically allocate to a CVM. The formula is available RAM minus 16 GB, limited to a maximum of 256 GB. Let me repeat that because it's important. Total RAM minus 16, capped at 256. So if you've got a beast of a host with 512 gigs of RAM, Foundation is not going to give the CVM 496 gigs. It hits that ceiling and stops exactly at 256. Make sure you memorize that maximum cap.
Finally, Section 4, Key Facts to Memorize. Let's cover the exam essentials.
We are in the home stretch now. Let's distill all this down into the pure, high-yield facts you need to commit to memory for the NCP-MCI 7.5 exam. First, know your source of truth. Table 16, CVM field specifications. It lives in the Advanced Administration Guide. If an exam question asks where to find the baseline logical core and vRAM specs per platform, this guide is exactly where you look. Not the release notes, not the hardware manual. The Advanced Administration Guide. Next, lock in the number 20. This is the absolute bare minimum CVM memory in gigabytes permitted anywhere in the Nutanix ecosystem. But remember the context from earlier. This 20 gig minimum is strictly valid only for single-socket robo or edge deployments. For a standard x86 deployment, your baseline is already going to be higher. Then we have the magic number for high performance, 48. This is the critical memory threshold in gigabytes for any deployment running Blockstore with SPDK on NVMe or Optane hardware. This is also the exact number the Foundation tool will automatically auto-raise the memory to if it detects an SPDK deployment that was accidentally undersized. So let's review to bring it all together. Your absolute minimum CVM memory is 20 gigs for ROBO and Edge. The moment you use SPDK with NVMe, that minimum instantly becomes 48 gigs. If you forget to set it, Foundation auto-races it to 48, but again, only if SPDK is actually deployed. At the very top end, the Foundation auto allocation cap is 256 gigs, calculated as total RAM minus 16. And finally, all of these per-platform specifications are officially housed in the Advanced Administration Guide. I'm going to leave you with this final thought to ponder. If you miscalculate your CVM resources, are you starving your entire cluster's true potential? The CVM is the engine of your hyperconverged infrastructure. Mastering these sizing rules ensures you aren't just checking boxes to pass the NCP-MCI 7.5 exam, you are actually architecting resilient, high-performing environments in the real world. Thank you so much for joining me for this explainer. Study these numbers hard, and I'll catch you next time.